let's move on to ELR 3.1. Now I'm moving pretty quickly, so you can pause this at any point in time. The acceleration. So I know that ELR 3.1 has to do with the formula delta V over delta T. So what is the acceleration of an object that takes 20 seconds to change from a speed of 200 to 340? So I need to know that the change in velocity, by the way, I want to write my formula, is equal to 200 up to 340. So it went up 140. It takes 20 seconds to do that. That gives me 7 meters per second, which is A. Derek is the driver of a train moving at 10. He applies the brakes and slows down to 1.5, and he does it in 20 seconds. So he's slowing down this time. So I know that I'm going to take actually 1.5 minus 10. So it ends up being a negative 8.5 over 20 seconds. And that gives me 0.425 meters per second. Now remember, I did not write my formula. Let me write my formula over here. Remember, to get full credit on these, if they're open-ended, you want to write delta V over delta T as the formula, then fill in the numbers, then write the answer. Falling objects drop with an average acceleration of 10. So this time I'm given A. If an object falls from a tall building, how long will it take before it reaches 42? This is its final velocity. Okay, so I'm trying to find out time, which is how long. So I know that A equals delta V over delta T. This time I'm given A, which is 10. My change in speed is 42 because the object is dropped from the building, it falls. So my change, it goes from 0 to 42 over T. Okay, so I'm going to cross multiply. I'm going to pretend this is over 1. I'm going to cross multiply. 10 times T is 10T. 42 times 1 is 42. I divide both sides by 10. I'm running out of room here. And I get 4.2 seconds. That is my final answer. All right, Matt's new puppy named Waffles was running at 20. It's a very fast puppy. And accelerated to a velocity of 5. Now, remember in physics, even if it's slowing down, we call it acceleration. We just give it a negative acceleration. It does it in 3 seconds. What is the acceleration? So it went from 20 to 5. That's negative 15. Oops, I need to write my formula. Negative 15 over 20. I get out my handy dandy calculator. .75 meters per second. Okay. All right, that's ELR 3.1. Now let's look at ELR 3.2 through 3.4. So an example of, oops, too far down, sorry. An example of Newton's second law is anything that involves a changing mass and its relationship to force and acceleration. Or it could be a changing force and relating it to mass and acceleration. Or it could even be a changing acceleration. It's basically any example where you talk about how changing one thing would affect the other two. Okay, it's a lot like your force equals or force mass acceleration oh my videos that you made. All right, what is the force of gravity? So I'm figuring out a force here at the Earth's surface on the following masses. So I know that F equals ma. My first step is to write out the formula. So force equals mass times A. Now if the force is caused by gravity, A is going to be 10. So I get 750 newtons. This one's a little different because I need to convert it into kilograms first. So what I know is that I move the decimal to the left, or I basically divide by 1,000. So this is really 0.454 kg. So F equals ma. F equals 0.454 times 10, and I get 4.54 newtons. Okay? So basically that's how much gravity would be pushing down on those masses. Now, number 3, this one a lot of kids got stuck on. Emma is an astronaut who has traveled to Mars. While there, she finds that Ralphie the Rock accelerates at 3.6. So this is the acceleration. She also finds that a Newton scale reads 180. So if this is acceleration and this is force, we automatically know I'm probably solving for mass. But let's read the question. What is her mass as determined on the surface of Mars? Hint, if a rock accelerates at 3.6, then a person accelerates at the same rate as well. Okay, so this is just a tricky way of me telling you the acceleration on Mars. So I write out the formula. F equals ma. 180 equals mass times 3.6. I get out my handy dandy calculator because I'm going to divide by 3.6 to solve for m. And I get that mass equals, technical difficulties, 50 kg. What would the Newton scale read if she stepped on it on Earth? Hint, her mass stays the same, but Earth's gravity pulls down more. So this mass stays the same, but now my acceleration changed. It's no longer 3.6. So now I'm going to say the force, which is what the Newton scale would read, is the mass, which is 50, times the acceleration on Earth, which is 10. So it's going to read 500 newtons. And the question is, does that make sense? And if it was 180 on Mars that has about a third of the acceleration, then yeah, 500 totally makes sense on Earth. Okay?